Algebra 2, Lesson 5.8, Analyze Graphs of Polynomial Functions. This first page is really a summary of some of the terms and ideas we've done recently. When you have a factor, a binomial factor of a polynomial, it indicates that k is a zero of the function. And when you substitute k into the original polynomial, it gives you 0 for an answer. Those two statements are directly linked together. Lastly, when the polynomial is graphed, you will see that the polynomial crosses the x-axis at k. k0 is a point on the polynomial. It's where the graph crosses the x-axis because k is a zero of the function, which means when you put k into the function, you yield a value of 0. The way you know how many zeros of function you have is based on the degree of the function. The degree simply refers to the largest exponent of all of the terms in the polynomial. And this has been formally proven in the fundamental theorem of algebra. You've known it all along, even in Algebra 2, when you dealt with quadratic equations, your exponent, your largest exponent, in other words, your degree, was 2, and you were looking for the 2 possible solutions. So as we look at this equation, the degree is 3, which means there are 3 zeros of the function. As we further expand upon this, when this is graphed, we see that there are 2 turning points. A turning point, just as it says, is where the direction turns. This parabola over here is going up, 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 up. It turns and it starts going down again. It's going down and it turns and starts going back up. There are 2 turning points. Now, even without looking at the graph, we know the number of turning points because the number of turning points is always the number of zeros minus 1. And that'll be an important thing to be aware of because there might be times when you graph something on your graphing calculator and you can't see the full graph. You won't know if there's more of the graph or not. But if you know the number of turning points and you can see that you are not witnessing those turning points on your screen, you're going to have to make some changes. We're calling this point up here the local maximum because it's higher than all the points nearby. This polynomial actually continues going on infinitely up here, so the maximum is, well, up there in infinity, but we're calling this the local maximum. This is the local minimum because it's lower than all the other points that are nearby. Let's take a look at another example. Keep in mind, these turning points are important. So you know the shape of your graph if you know the degree of your polynomial. The degree minus 1 is always the number of turning points. This first statement up above here is probably the most important one to keep track of. You can look at the reverse idea and say if you know the number of turning points, you can add 1 and that gives you the degree. But we're going to focus mostly on this upper statement. So with this function here, our degree is 4. That's telling us that there will be 4 x-intercepts. There will be 4 solutions. There will be 4 zeros of the function. And then the number of turning points, that's simply 4 minus 1. So as you see the graph here, there indeed were 3 turning points. 1, 2, and 3. We'll investigate with our next problem how to use a graphing calculator to identify the ordered pair that represents the minimum and the maximum. Next example. I want you to graph this on your graphing calculator. So in the y equal to, using the y equal to button, the topmost left, enter this equation. If you forget where the variable x button is, it's the button next to the green button. It'll have an x, a t, and a theta, even an n on it. Hit that and that'll give you your variable x. So I want you to input this entire polynomial and then hit graph. When you hit your graph button, your graph should look something similar to this one. You can see there are 2 turning points. Just as if we had multiplied this out, we would have had an x cubed, just as our degree would tell us. How do we identify what that ordered pair is? We're going to use our calculator. There's a feature on our calculator that will calculate an ordered pair for us that is the minimum and that is the maximum point. Let's start with the minimum point. So to access this calculate feature, it is the second function of the button that is to the left of your graph button. Hit second, hit that button, and you'll see all the different features that your calculator will calculate for you. Arrow down to minimum. Once you hit enter, you'll see your graph again, and you'll see a blinking cursor. Identify where your little blinking icon is, if you will, and note the question that they're asking you down the bottom left. It says left boundary. It's asking you, is your blinking cursor on the left side of that local max or local minimum? If it is not, use your left and right arrow to move it somewhere over here on the left side of that local minimum. Once you have your cursor there, hit enter. Down below in that same left-hand section, it's going to prompt you for the right boundary. That means move that blinking cursor anywhere on the right side of that local minimum. You don't need to go too far away from that, your local minimum point, but move it officially to the left side, to the right side, excuse me. As you hit enter, the final question will ask you is guess. It's saying, are you ready for me to guess what this local minimum point is? Hit enter, and that will show you that the calculator has identified for you that ordered pair of that local minimum point. You can repeat this process for the local maximum, but you have just identified what that ordered pair is for the local minimum. Let's repeat the process for the maximum and check back this ordered pair. So you're going to hit your calculate button, arrow down to maximum. You will get the prompt down below that once again says, are you on the left side of that local maximum? Move your cursor if it's not there already. Hit enter. It's going to prompt you for the right side of the maximum point. Move your cursor to the right side. Hit enter. And then it'll prompt you, do you want it to guess? Yes, you definitely want it to guess. So hit enter one more time, and you should see the local maximum is the ordered pair negative 7.9, 2.1. How can this be helpful to us? Let's think of the activity that we did yesterday when I handed everyone a blank piece of paper and I challenged you to fold it to make a box that would have the greatest volume. Now everyone started out with the exact same length and width of your paper. The really only true variable in this is the height. All of you were picking different heights to calculate what the volume of your box would be. Well, this time we have a piece of cardboard that's 20 by 16. If this original width is 16, the width of our box is going to be on this yellow line between here and here. This can be calculated by taking 16, the original length, minus the x that was folded up when we folded up the top section of the box, minus another x as we folded up the bottom section of the box. So my width of the box can be calculated as 16 minus 2x. The same holds true for the length of your box. This piece was originally 20, but if I want to know the length from here to here, I'm going to take 20 minus the x that I folded up on the left side, minus the x that I folded up on the right side. I just took 20 minus 2x. So the equation for the volume of your box that you want to make is the length is 20 minus 2x, the height is 16 minus 2x, and the height is x. Let's put that into the graphing calculator. Now you are not going to see a shape that looks like mine here. Mine's been adjusted already. Your graph, your screen from your graphing calculator, you're going to see a couple lines over on the right-hand side, which is telling you that your graph is so large it does not fit in the window that you have. Hit the window button. It's the button next to the y equal to. Notice you have a preset minimum and maximum for your x-axis. Your x-axis goes from negative 10 to positive 10. Your y-axis goes from negative 10 to positive 10, and the scale is a 1, meaning each tick mark that you see in your graph counts by ones. We need to make some adjustments, and there's no set rule for how to come up with this. It's a little bit of guess and check, but if you look back at your graph, hit your graph button again, you will see that there's nothing from your graph over where the x's are all negative. You really don't need that part of that part of your x-axis. So let's go back to your window and let's change your minimum and your maximum of the x-axis to -2 and 14. And let's count by 2's. Now the y is more of a challenge, and it really does require a little bit more playing around. This is where I say, go big or go home. Pick some really large numbers for the range of that y-axis. I often start with -50 for my minimum and +500 for my maximum. And because those numbers are so large, I'm going to use a scale of 50. Each tick mark is going to be 50 units. Hit graph one more time. Now you can see the actual shape of your polynomial. You can see that local maximum. You can even see the local minimum on your screen. So one more time, you're going to have your calculator calculate what that local maximum point is. When you go through that function, calculate maximum. Ask for the left boundary, move your cursor to the left side. You'll ask for the right boundary, move it to the right side. Finally, hit enter, and it'll tell you that this local maximum is 2.94, 420. So just a quick recap. What was x again in your equation? X represented the height of your box. What was your equation actually equal to? This equation was your volume calculation. The volume was length times width times height. So the y of that ordered pair of your maximum is the volume. Now 2.94 inches, we're going to round up to 3 inches as we're actually thinking of creating a box. And indeed, when you take 3 times your new calculation for the width, new calculation for the length, you will get 420 for the volume of your box. So this idea of calculating a local maximum helps you maximize values of an equation. In this case, it maximized our volume. This example is going to be one of the learning targets that you will be tested on in Chapter 5.